In this video, we're going to look at the binomial distribution. We're going to graph discrete probability distributions. We're going to compute binomial probabilities using the binomial probability formula, a binomial distribution table, or a graphing calculator. Well, we're not going to use a graphing calculator. You can, we don't. We're going to use the binomial probability distribution to solve real-world applications. We're going to compute the mean and standard deviation for a binomial distribution. There were certain things that identify a binomial distribution. First of all, there is a fixed number of trials. So we want to think of trials as the repetition of an experiment. This is when you're tossing a die or flipping a coin. There are only two possible outcomes. So you either have success or failure for each trial. So this is where we talk about flipping a coin. You could talk about rolling a die if you have the die. The success is rolling a 3. The failure is rolling a not 3. We have P and Q, where success is P, Q is the complement or failure. And we know that P plus Q is equal to 1 here, or we can say that Q is equal to 1 minus P. That's what we've been using when we do complement up until this point. The trials have to be independent. That means flipping a coin one time should not make any difference of flipping a coin a second time. We have to have identical conditions because the trials are independent. The outcomes of one trial does not help or stop predicting the outcome of the next trial. Another way of saying this is for each individual trial, the probability of P of success and probability Q of failure remain the same for each attempt that we are doing. So some things about the binomial random variables in general. Categorical data is collected for each trial, so either you have heads or tails. The binomial random variable X, the capital X, is recorded at the end of all the trials. It's quantitative discrete because it counts the numbers of success. Now remember, when we're doing this, we're counting success. The outcome success and failures are words, not numbers. The outcome that is being counted is always success. P and Q are probabilities that add up to 1, and they are complements of each other. So when you're figuring out P, you can think of this as happening on a single trial. When you want to find Q, then Q is going to equal to 1 minus P, which we talked about up here. And even though there are only two outcomes, it is rare that they have equal probability of occurring. In other words, typically P will not equal Q. It's not a 50-50 type chance. So let's take a look at the first example. The State Health Board is concerned about the amount of fruit available in school lunches. 48% of schools in the state offer fruit in their lunches every day. This implies that 52 do not. What would be the success in this case? Well, since we're concerned about the fruit available in schools, the schools who offer fruit would be success. So P is success, which in this case is the schools who offer fruit. They're giving us, in this case, 48% is giving us the percent of schools who offer that. So our P would be 0.48. So remember, probabilities are between 0 and 1. So 48% is a 0.48. That means Q would be a 0.52. And Q is a failure, which is the percentage of schools who do not offer fruit at lunch. 65% of people pass the state driver's exam on the first try. A group of 50 individuals have taken the driver's exam is randomly selected. Give 2 reasons why this is a binomial. Well, so first of all, you have a fixed number of trials. So that's kind of important. 50 individuals are selected. And the other thing is that one individual's getting a license is not going to prevent the next individual from getting a license. And it's a pass or fail. You either get your license or you don't. So this is binomial because we have 50 individuals. And the first person getting a driver's license does not affect the next person getting a driver's license. So this is why that's a binomial. Lacrosse team is selecting a captain. The names of all seniors are put into a hat, and the first three are drawn will be captains. The names are not replaced once they are drawn, and you want to see if the captains all play the same position. State if this is binomial, yes or no. Well, in this case, it is not a binomial because we have without replacement. So if you have, say, 10 people and you are drawing 3, then after you draw that first one, you now are drawing from 9. And so choosing the first one is going to change the probability of who gets selected on the second attempt. So this is not binomial. It does have a limited amount of trials, but the one trial is going to affect the next one, which is going to affect the next one, and so this is not going to be binomial. The outcomes of a binomial experiment will fit a binomial probability distribution. The random variable capital X is the number of successes obtained in trials, so we noted as this capital X is in the squiggly line. It means that it is approximately equal to, kind of equal to, it will be considered a binomial. And notice with a binomial probability distribution, it is with a capital B, where N is the number of trials and P is the probability of success. So this is the notation. And then when you are looking at the probability of success, there's a couple of ways of doing it. So you have P of X is equal to N choose X multiplied by the probability of success raised to the X, and then 1 minus the probability, which is Q, and then it's N minus X. Some notation is that you're going to have X is equal to 4, or you might see it as just a random A. So I want to show you that that could be A. That means the probability that X is exactly A. If it is, if it has a number, the probability that X is less 4 or less, or at most 4, you might see those words. X is greater than, and you see the P out front. This is the probability that X is 4 or more, or at least 4, and X is greater than 4, which is 1 minus the probability of X less than or equal to 4. The probability that X is greater than 4 but not including 4, and of course when X is strictly less than 4, then it's a probability of 3 or less. So according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. So suppose there's a random sample of 20 car-owning households. What is the probability that exactly 5 households have 3 or more cars, where P of X is equal to 5? Now I said there's actually 2 ways to get this, and so we're going to do the first way, which is using this formula. So if I use this formula, I'm going to have P of X is equal to 5, which is going to be equal to the, we have 20 cars, so we have 20 choose 5. The probability of success is 0.35. And it will be raised to the 5th power. And then I have 1 minus 0.35. This is my Q. And then I'm going to have the 20 minus 5. Now, I can put that in my calculator, but I said there's another way of doing that. Well, the other way that we can do that is with a spreadsheet. So in Excel, we have this binomial dist. So if we do an equal symbol in the cell, we do binomial by binom dot dist, and then it's going to ask me a bunch of stuff, right? So in this case, I would need to put in some, I'm going to explain what all this is, A, N, P, and then we need to be either put true or false. Okay. So what is A? Well, A is the number of interest. So if I were to put this in my spreadsheet, I would be putting in an equal sign binom dot dist, and the number I'd be putting in is 5 because I'm interested in exactly 5, so I put in 5. I have 20 pieces of data, and the probability of getting success is 0.35. Now I've got to decide whether or not I'm going to do true or false. Well, I'm going to choose false, so I'll type in false. And the reason I would type in false is because if I type in true, then it's going to be looking for everything to the left, the area underneath the left of the binomial curve. So false is just exactly, I want it exactly equal to, I don't want left or right, so I want exactly equal to, so I'm going to use false. So I can use this formula here, over here, or I can use a binomial dist. So if I look at B, I'm going to do it both ways. I'm going to do it with the formula that is given to me up above, and I'm also going to use it with a binomial distribution, and I'll show you what you need to do to make that adjustment. So if I'm going to use P of X, which is less than 4, then I would have to do 20, choose 1, 0.35 to the 1, 1 minus 0.35 to the 20 minus 1, plus 20, actually I should make that smaller, 20 choose 2. So 20 choose 2 of 0.35 raised to the 2 times 1 minus 0.35 raised to the 20 minus 2, and I'd have to do that up until I got to the third one, and then I'd be done. So that's a problem because that's a lot of work, and I'm not inclined to do that. So I'm going to do it with a binomial dist. So I'm going to do equals. I'm going to do binom.dist. Now, if I'm going to be using the binomial distribution, by default, what it's doing is it's actually choosing all the things to the left. Okay, so since it's choosing all the things to the left, I'm going to use the binomial dist, but I'm not going to go to 4 because it will be inclusive of 4, and like I said up here is I really actually need to go one less. So to use a binomial distribution, and I don't have inclusive on 4, I have less than 4, then I'm going to use a binomial dist, and I'm going to put 3 in here, not 4, and I'm going to do 20. I'm still going to do 0.35, and now I'm going to hit true. So what the true does, if you spell it correctly, which clearly I can't seem to, what the true does is it takes, put that parenthesis, it's not a comma. It says I want to add up everything prior to. That is the first one, the second one, and then of course I would have had my third one had I done it with this formula. So I don't include 4 because it's not included 4. Cool. So binomial dist will work, and it'll give you the exact same answer as if you were to have wrote all of this out by using the formula up above, doing 20 choose 1, 20 choose 2, 20 choose 3. Cool. Don't want to do that. That's a lot of work. So then what is the probability of at least 4? That means I get to include 4, so I get to count 4 on up. But here's the thing. If I were to have done writing this out, the probability of x is greater than or equal to 4, then that means I have 1 minus the probability of x is less than or equal to 3. Because remember, I don't have any in between. Because we're looking at the success, and this should be a 4. So it is inclusive, but I'm going to actually go 1 down again for the binomial distribution in this particular case. If I were to write out the formula using the formula up above, I would have done 1 minus, and then I would have had 20 choose 1, and it's stuff that goes with it. You would have had 20 choose 2, and multiply by what it needs to multiply by, and then you have plus a, I'm just going to erase this. Let me erase this here. And then I would have had the next term, which would have been 20 choose 3, and what gets multiplied to it. So this would take into account that I want 4 or more, which means I need to have 1 minus 3 or less. So here's my first, second, and third. This is the probability of choosing 1, choosing 2, and choosing 3. Okay, so I'm going to use the binomial distribution, and so this is going to be equal to 1 minus, and I'm going to do binom. Now remember, I'm doing the equal sign in my spreadsheet, my binomial.dist, and I'm going to use 3 because I want to strip off 1, 2, and 3. So I'm going to have 3, and then I'm going to have the 20, and then I'm going to have the 0.035, and then I'm going to do true. Now, what this does, right, is the same thing as if I were to have wrote it all out, and then using that formula, which is, this formula, which is up above. And that's how I do it, which is a lot of work. I'm going to do the binomial distribution to help me do it. So then that gets us to the expected value and the standard deviation of the binomial random variable. So remember, x is the binomial random variable, which means here is our x is our random variable, capital X. It means it's distributed as a binomial where you need to know an n and a p. P is probability of success. And then our mu is going to be n times p. That is our mean, our expected value. Remember, expected value is always using mu versus x bar, because x bar is the actual calculation. Mu is the expected value, which is like thinking about it as the population, n times p. And the standard deviation, which is sigma, is going to be n multiplied by p multiplied by q. And there was a couple of things that we need to talk about. Is as a general rule of thumb, this has to hold true, that n times p multiplied by 1 minus p, which is q. So n times p times q has to be greater than or equal to 10. You might see this as n times q has to be greater than or equal to 5, and n times p has to be greater than or equal to 5. So you might see it broke up slightly. But what we do know is that we have to have symmetry, usually, and this also has to hold true. The expected value, or the mean, of a binomial random variable is the number of successes you would expect in n trials. And the standard deviation from the mean is often considered a good rule of thumb to identify any unusual or extreme values in a bell-shaped distribution, including binomial distributions that exhibit bell-shaped characteristics. So let's take a look at this example. Both, according to the Experian Automotive, 35% of all car-owning households have 3 cars or more. A random sample contained 400 car-owning households. Determine the mean and the standard deviation of the number of car-owning households that have 3 or more cars, round 2 decimal places. So they're telling me that it is a success of owning 3 or more cars. Failure is 1 minus that. So this is a binomial distribution. That means my mu, using the formula up above, as we know, is just going to be n multiplied by p. So n is 400 and multiplied by 0.35, which gives us 140. So another way of thinking about this is if I take 140 divided by 400, I'm going to get 0.35. My sigma, which is my standard deviation, is going to be the square root of my 0.35. 1 minus my 0.35, that's my q, and then of course my sample size, which is 400. I get that to be 9.47. Now we need to determine if the probability distribution is approximately bell-shaped, and the one way that we can do that is this. So we want to make sure that holds true, so we take our 400 and we multiply by our our p, which is 0.35. And then 1 minus 0.35, and then we are confirming that this is equal to or greater than 10. This happens to equal 91, which is greater than 10. So it is approximately bell-shaped, and we get everything that we get with bell shapes will hold true for this example. Now, suppose you have 60 households of the 400 state that they have 3 or more cars. Is this considered unusual? So to decide whether or not this is unusual or not is we're going to look at the z-score. So the z-score, if you remember, is going to be x minus mu divided by sigma. And we're using mu and sigma here, not s and x bar, because this is expected values. And so for us, we have the piece of value that we're looking at, which is 60, minus our mu, and our mu was 140. And our sigma we found to be 9.47. We end up with a negative 8.45. Now, a z-score of a negative 8.45 is pretty darn low, and it indicates that the observed value is gonna be below the mean, which means it's actually significantly below the mean. That means that only having 60 households with 3 or more cars out of the 400 is very unusual and very unlikely to occur. So z-scores tell you how far away you are from the mean, and usually we want z-scores to be maybe 1, 2, 3 at most, or -1, 2, -3 at most. The fact that this is much larger than -3, that tells us that this is pretty unusual. So when you are in this chapter, specifically this question or this section, is you might want to have a spreadsheet that looks something like this to add to the previous spreadsheet in, like chapter 4 labeled, or you could label each one as 4.2, 4.3, or whatever. I make a note to myself on my spreadsheets. Note you must choose one less if it's less than, or one more if it's greater than, unless it states inclusive in the question in this chapter, this particular chapter. So you're going to use this if you only have 2 outcomes, N is the sample size, P is the probability. I like to label everything so that I know what I have later. Now here I also like to put green to remind myself I'm actually putting in values in there, and then the rest is going to be calculated. So if it's not in green, then it has calculation. So in this case, what I'm asked for is 11. So maybe I'm looking at the number of interest is 11, or it could be less than. So if it could be 12, and I'm looking actually at 12, and so I'm going to use 11. So the probability of x being less than 12, I use 11, and this is the probability of the value being less than 11 or less than 12. This is probability of it being more, 12 or more, and this is the probability of it being exactly 11. So then if I want exactly, I'm actually going to have to put in 11. So this is the only time in which I'm going to do one less, is when I have exactly that amount. So if I want exactly 11, I'm going to put 11 here. If I want exactly 12, I'll put 12 here and only use this information. If I want less than 12 or less than or equal to 12, I'm going to put in 11, and then I'll use these 2 here, depends on what it is that I'm looking for. And then, of course, if I have a sandwich, right, so I'm going to have a sandwich between this one and this one. I should have actually highlighted this in green, so maybe I'll just do that really fast here. So this actually should be highlighted in green because I'm going to be entering a value there. So if I have this entering this value, and then I have, so I have the sandwich of less than, I have it greater than, I have it sandwiched between this A number and this B number. And then if I want to know the number that would land in a certain percentile, which I didn't talk about in this video, so it must be in the next one. If I want the 95, what data piece is the 95th percentile, I would put in the percentile, and then this will tell me the data piece. So in this case, it would be 14. Notice that here I'm using the binomial invert, and then I need NP and the percentile. So I'd be grabbing the N cell from up here. I'd be grabbing the P cell from up here, from right here, and then I'd be grabbing the percentile, which is this number right there. We're going to go over this in class, but I would highly recommend coming to class with this somewhat filled out, using my numbers. Make sure you're getting the same numbers as I'm getting, because we probably will not have time in class to fill this out completely. So I would highly recommend that you have this done prior to class when we cover this in class. That's it for this video.